All right, this problem is just drilling, giving you guys more examples, more different things that you can see. Some of these are a little messier just to give you some more practice. I highly recommend for this video, watch it with a piece of paper. Like, it's a good habit to be taking notes anyway, but especially here, pause the video when I write down the problem. Try to do it on your own using the techniques from the last video. And then if you get stuck or if you want to see the solution, then use the video. That's going to be infinitely more beneficial, I promise you, unless you're really lost that you can't even start. Okay? Please do that. That is going to be beneficial for you. Example 2, evaluate the following limits. Part A, the limit as x goes to infinity of e to the 1 over x minus 1 over 1 over x. Oh, I forgot to mention kind of one of the ways that you can see how L'Hopital's rule works. Like, it's not a proof, but essentially it has to do with linear approximations. So if you look at the equation of a tangent line of this blue function f and this orange function g, well, we have the tangent lines at this point, this other blue function and the slightly green function. And if you just look and model these functions by their tangent lines, you can actually simplify that limit and get some cancellations. And you're just going to get the product of their quotients. All right. The book has some more information about this. Like, you can just see it right here. And then there's also a small mini proof for a nicer situation. But we're not going to spend time going over that here. But if you're curious where it comes from, the book has some good information. So let's try to use direct substitution. If we tried to use direct substitution, it's a little weird since it's infinity. But we'd have something like this. If we use direct substitution, and again, we haven't talked too much about direct substitution for infinity, but think about it. Let's look at the denominator. 1 divided by an infinitely big number should be 0. 1 divided by the biggest number you can think of should practically be 0. And that's the same for the top as well. E to the 0 is 1. So this is one of those indeterminate forms. 0 over 0. Top is differentiable everywhere on its domain, which is everywhere except for 0. Bottom, continuous everywhere on its domain, everywhere except for 0. We can use L'Hopital's rule here. So this is going to equal, by L'Hopital's rule, the limit as x goes to infinity of the derivative of the top divided by the derivative of the bottom. Remember your derivatives. The derivative of an exponential function is itself. But because we're not just taking the derivative of e to the x, it's e to something else, we have to use the chain rule. Multiply by the derivative of 1 over x, which is negative 1 over x squared. And on the bottom, we also have the derivative of 1 over x, which is also negative 1 over x squared. Now you could take some time simplifying this, but also notice that we have the same thing in the top as in the bottom. Everything's fully factored. There's no addition or subtraction. So they actually just fully cancel. And we just have the limit as x goes to infinity of e to the 1 over x. And now again, we can use that direct substitution logic. As x goes to infinity, what happens to 1 over x? It goes to 0. And we can use the function composition theorem for limits to say that this is just e to the 0 or 1. That was one of our theorems in chapter 2, function composition, when one function is inside of another function. All right. And again, you can also kind of evaluate this in steps. As x goes to infinity, we kind of have something like this. What's 1 divided by an infinitely big number? 0. That's sort of what's happening here. More technically, it's the function composition theorem, but usually we're not going to be writing that or proving it exactly. So hopefully, if we graph this, the limit is equal to 1. Let's look at this. Let's visualize it. e raised to the 1 over x minus 1, all divided by 1 over x. As x goes to infinity, as x gets infinitely big, what's the function value doing? It's getting close to 1. Also, this is a funny looking function. Wait, why does it say the function is defined at 0? The function should not be defined at 0. I think Desmos is maybe getting a little confused. Let's do another one. Part B, the limit as x goes to infinity of the sine of x minus x over x squared. Sorry, the limit as x goes to 0. I was like, wait, this is getting into the next video. The limit as x goes to 0 of this. Well, it's, again, the top is continuous, the bottom's continuous. Let's try direct substitution first. Always try direct substitution first. It's always the easiest where it applies. So sine of 0 is 0, minus 0 is 0, divided by 0 squared. Okay. We've got differentiable functions with an indeterminate form on that limit. If we try to use direct substitution, it's an indeterminate form, 0 over 0, or infinity over infinity. We can use L'Hopital's rule. The L'Hopital's rule tells us that this limit is the same as the limit of their derivatives. Each individual derivative, derivative of the top, divided by derivative of the bottom. Cosine of x minus 1 over 2x. Great. All right, now we can use direct substitution. Let's plug in 0. Cosine of 0 is 1. Oh no! We got another one! I snuck this one in there. It's another indeterminate form. It's just like derivatives. Sometimes you got to do it again. All right. It's not too bad though. So you might ask, Jason, if L'Hopital's rule didn't really help us the first time, is it going to help us the second time? Look at the denominator. We had an x squared, and now we have a 2x. And if we took the derivative again, we'd only have a 2. So I think the next one's going to be the last one. All right. I love moments like that. They're fun in the classroom too. I just have to imagine your guys' groans. That gives me life. Let's use L'Hopital's rule again. Top is still continuous. Bottom is still continuous. We still have an indeterminate form. Derivative of the top is negative sine of x. Derivative of the bottom is 2. And now we can use direct substitution. Sine of 0 is 0. We're going to get negative 0 over 2, which is just 0. As x gets close to 2, this function gets close to 0. Let's see that. Sine of x minus x divided by x squared. Hey, not you. You all divided by x squared. As x gets close to 0, look at that function value. Function value is getting really close to 0 at this hole. Notice that all of these have been removable discontinuities, except when x is going to infinity. Let's do another one, part C. It's just 5 examples in this video. That's all it is. The limit as x goes to infinity, sorry, I keep saying that. The limit as x goes to 0 from the right of the natural log of x divided by our good friend cotangent. You're really going to have to remember all of your derivatives from chapter 3. This is good practice for like a final. The limit as x goes to 0 from the right of the natural log of x over cotangent. All right, so these ones, they're still continuous everywhere on their domains, but I don't know if anyone remembers the graph of cotangent of x, but its domain is a bit of a tricky little guy. But remember, it doesn't have to be continuous at 0, which is good because cotangent is not continuous at 0. Doesn't have to be differentiable at 0. Just has to be differentiable around 0. And yeah, every single point on this graph is surrounded by a differentiable section, even if the point itself is not defined. And that's all we need for L'Hopital's rule, that in an indeterminate form. So if we try to plug this in, the natural log of 0, as we approach from the right, is negative infinity. Remember your graph of natural log. It looks like this. Cotangent from the right, you might not remember cotangent, but as x approaches 0 from the right of cotangent, is positive infinity. So it looks like it's going to be a negative answer. It looks like it's going to be negative, but the fact of the matter is it's an indeterminate form. Even if we think it's negative, we don't know what value it's going to be. That's the whole thing about indeterminate forms. So differentiable functions around 0, not at 0. Differentiable functions with an indeterminate form. What are we doing? We're using L'Hopital's rule. This is the limit as x goes to 0 from the right. Remember, if you're ever curious about which direction, from the right is from the positive numbers. From the left, that's coming from the negative numbers. That's how you can remember. Oh, I need a bigger eraser than that. All right, so what's the derivative of the top? 1 over x. What's the derivative of the bottom? Secant squared of x. Great, and now let's use direct substitution. We plug in 0, we get 1 over 0. Uh-oh, I don't like where this is going. We plug in 0, we get secant squared of 0. Secant squared of 0 might be fine. Cosine of 0 is 1. So secant is a reciprocal. That's going to be 1 over 0 divided by 1. It's still 1 divided by 0. Let's simplify a little bit, because this is a big complex fraction. We don't want to use L'Hopital's rule again. And we don't have to worry about whether it's positive infinity or negative infinity. Because here, as 0 from the right, now it looks like it would be positive infinity. Whereas before we thought it'd be negative. Let's save ourselves a headache and just simplify this a little bit. L'Hopital's rule takes away a lot of the guesswork. Well, this is just 1 over x divided by secant is the same as multiplying by cosine. Right? Dividing is the same as multiplying by the reciprocal. Okay. This is the limit as x goes to 0 from the right of cosine squared of x. Oh, the limit, the derivative of cotangent. I was so confused. I was like, why does it look like it's positive now? The derivative of tangent is secant squared. The derivative of cotangent is cosecant squared, is negative cosecant squared. Woo! That makes me feel a lot better. Negative cosecant squared. So this is going to be negative sine squared up here. Hope y'all were screaming at your monitors for that. All right, sine squared is 0. Yeah, this is still a problem. And then this down here is just going to be sine squared. Like so. 0 over 0, indeterminate form. Too bad. But if we use L'Hopital's rule again, and we still have a negative, Jason. If we use L'Hopital's rule again, the bottom is going to go away. Ah, that would be great. So let's do it. Continuous functions, 0 over 0, indeterminate form. It's L'Hopitalin time. I like that. Derivative of the top, we're going to have to use the chain rule. Power rule first. It says bring down the power, subtract 1 from the power. Multiply by the derivative of the inside, which is cosine of x. The derivative of the bottom is just 1. Remember that sine squared of x is really just sine of x squared. So this is what we're using the chain rule and the power rule on. The squared is the outside function, even though it doesn't look like the outside function when we write it like this. All right, are we done with this, Jason? Can we use direct substitution already? I think so. That denominator is looking real nice. We're going to get -2 times the sine of 0 is 0 times the cosine of 0 is 1. Great. That's just 0. So I said it's negative infinity over positive infinity. It's probably going to be some negative number. Well, it's not. It's just 0. And that's weird. And the reason why is because one of these infinities is growing faster than the other infinity. So the top is going to infinity, but it's going to infinity slower than the bottom is. And there's a cool thing at the bottom of this section that talks about how fast things are going to infinity. But we're not really touching that in this class, but it's fascinating and I want to, but I'm not going to. Y'all have enough right now, but it is cool. Let's visualize this. All right, we're looking at the natural log of x. I don't remember, wait, I don't remember what problem we're doing. Is it really the natural log of x divided by cotangent? As x approaches 0, yep, you can see. It's not actually defined at 0. Don't let Desmos fool you here. But the limit approaches 0. The function doesn't exist at 0. Oh, I guess cotangent. The limit as x goes to infinity of this quotient actually doesn't exist because cotangent repeats forever. So disregard the comment about growing to infinity faster. There are some things that do that, but in this case, it doesn't. Cotangent of 1 over x would grow faster as x goes to infinity. Yeah, they grow faster as x goes to 0. Anyway, there's something that I didn't explain it super well, but it is a related concept, but not as x goes to infinity. It was as x goes to 0. Great, box the answer, and let's move on. D, the limit as x goes to 1 of x squared plus 5 over 3x plus 4. Now I know y'all like L'Hopital's rule, but don't ride the train off the cliff. I don't think that's an idiom, but don't do it anyway. Don't use L'Hopital's rule here. L'Hopital's rule doesn't apply. Always try direct substitution. 1 squared plus 5 over 3 plus 4. Oh, that's just 6 over 7. There's no indeterminate form 6 over 7. L'Hopital's rule doesn't apply. So don't get tricked. If you can evaluate a limit the old-fashioned way, do it the old-fashioned way. Specifically, not only is L'Hopital's rule messier, it's wrong. It does not apply. Remember, L'Hopital's rule said we need the functions to be differentiable. We have that. L'Hopital's rule also says we need an indeterminate form. It's not just saying this works and is useful for indeterminate forms. This says it only works for indeterminate forms. Okay? And in fact, if we tried to use L'Hopital's rule, we'd be wrong. If we tried to use L'Hopital's rule, we'd get the derivative of the top is 2x. The derivative of the bottom is 3. As x goes to 1, we get 2/3. Well, that's wrong. The limit's 6/7. This is a continuous function. This is a rational function on its domain. So don't get too excited. Do not use L'Hopital's rule unless you can. Last example. The limit as x goes to 0 from the right of 1 over x. Again, can't use L'Hopital's rule here. We do not have an indeterminate form. Try to use direct substitution. We're going to get 1 over 0. That's not an indeterminate form. That's some kind of infinity. So you have to solve this some other way. One of the ways is knowing how 1 over x looks. This is one of our toolkit functions, we sometimes call it. And as x gets close to 0 from the right, we're shooting up this way. function's going to positive infinity. So again, L'Hopital's rule, derivative of the top divided by the derivative of the bottom, L'Hopital's rule would tell us that this goes to 0, but it doesn't. So don't use L'Hopital's rule unless you can. That's the final warning of this video. My very stern warning. Stern math professor Jason warning. Okay. Hopefully these examples help you out and you can work on that same chunk of problems. Best of luck, because in the next video, we're getting to some wackier stuff.